Hello and welcome, everyone. It's a big pleasure for me to take part in this conference. My name is Marcin Mosiolek. I am the lead AI engineer from SII Poland, and I really hope you will enjoy my presentation. Today, I would like to tell you how our team has dealt with a large-scale deduplication problem. I'm about to present how we built a solution that can quickly identify duplicated content by effectively searching among a huge database of documents. Everything I will describe relates to a real-life challenge that used to appear in the documents processing pipeline of a client-facing product. This talk will start with the business case so that all of us have a common understanding of the problem that we try to solve. Then in the consecutive parts, I will cover each of the steps we perform to develop the final solution, including contrastive representation learning and scaling up the solution to decrease the latency. I will also present the results and the next steps. So let's start. Let's start with the business case. One of our customers is a company called Dodge Construction Network, and it's basically the leading provider of analytics and software-based solution for the construction industry in North America. Dodge processes and analyzes a tremendous amount of construction-related information collected from the internet and provides the identified insights to the clients, such as architects, engineers, or contractors. It also maintains the most comprehensive and up-to-date information regarding the market. Hence, if you are, for example, a plumber company, and you look for a project in California, but you are only interested in such projects that rely on components from some particular manufacturers, you can ask Dodge and immediately get access to such projects. Primarily, Dodge extracts the information from free text documents that usually come as HTML snippets pulled from the web pages. As the data is collected from multiple sources, the same information might be collected numerous times. For example, two different pages may share the same information but use different wording or incomplete information. Let's consider two sentences visible on this slide. One coming from the service red and the other coming from the service blue. The sentence from red is, New York's famous skyscraper requires third floor painting improvements. The bids will be accepted starting the 25th of March. And the other sentence is, redecoration of one of the high-rise buildings floors at 5th Avenue, New York, bids start 25/03/22. As you can see, there is a lot of commonality between those two messages, but they don't correspond to each other in 100%, as they use different wording and provide various granularity of information. However, we as human beings, we can determine that those two sentences are very likely to refer to the same thing. So in other words, we had to deal with a deduplication problem. Otherwise, the data analyzed by Dodge wouldn't be reliable, and the analysis could lead to drawing false conclusions. For the purpose of the data analysis, the information from free text documents is extracted and stored as structured database records. Such entities like project titles, dates, and company names are extracted. And as we speak of entities extraction, we can't avoid a well-known topic called named entity recognition. Dodge has been using heuristics, regular expressions, and humans to extract the named entities in the past. And in some cases, it worked pretty well, offering very high precision. But as you know, it's hard to write a regular expression that covers all the possible cases, and some entities can't be captured this way at all. Therefore, we decided to build a transformer-based NER to enrich the data records with new dimensions. To construct a reliable training data set, we deployed a data annotation tool called Docano or Docano. I really have no idea how to pronounce it correctly. It's a simplistic, easy to deploy and configure tool, and it's trivial to use. As a user, you can simply highlight text and select the corresponding label, just as you can observe it on the attached video. So we worked with a dedicated annotation team of 3 persons that were supported by a subject matter expert. And the team was asked to label the named entities identified by Dodge as important. We took an iterative approach to collect the data. At first, our team annotated a small batch of data to understand the entities better. At this early stage, we also discovered many inconsistencies in the data annotation, which helped us define precise guidelines on how to annotate the entities. Moreover, we implemented some scripts to identify these discrepancies and some other scripts to fix those discrepancies automatically. Then we trained an initial model using the first batch of the data, and it appeared it already offered a decent performance for some of the entities types. As some of the entities were already identified correctly or required just slight modification, this could reduce the data annotation team's work. Hence, for the next iteration, we asked the data annotation team to keep labeling the data, but instead of presenting them blank documents, we presented them with the documents that were pre-labeled with our model. And we kept iterating like that in 1 week long sprints, including data annotation, data analysis, fixing, training the model, and pre-labeling the remaining documents. One thing that I would like to add at this point is we kept our NER model fixed and simply relied on Distill-Roberta based with token classification layer. So rather than modifying the model, we tried to collect and adjust the data. However, at some particular moments, we discovered that the approach we took got a lot of hype thanks to NRNG. And we also discovered that this approach got the proper name, that is data-centric AI. It basically means that you keep your model fixed and instead you work on improving your data. I used to think that our approach was quite typical in commercial machine learning projects, when one needs to deal with real data, what requires a lot of data preparation work, such as data collection, data understanding, data cleansing, data transformation, data normalization, and so on, to make machine learning possible and efficient. Therefore, according to me, data-centric AI is quite controversial once it's being sold as completely new paradigm by Andrew Ng. Meanwhile, I bet many engineers used to apply it on daily basis for years. However, the positive thing I can see is the data-centric AI hype may bring a lot of attention from academia, and maybe we will see some new powerful tools for data transformation or new approaches. To sum up, we managed to label roughly 10,000 documents and collect 180,000 entities. Our final model obtained 89% F-beta 0.5 score, which may seem like not a lot if you compare it to academia benchmark datasets. But in our scenario, we dealt with nearly 40 different types of entities rather than just very few. Moreover, some of them had a super type as a company name that could belong to an architect, construction manager, or a general contractor, and we are expected to know it as well. Okay, so now we already know how we constructed the named entities recognition system, and we can take a look how we built the records deduplication algorithm. Dodge used to rely on a semi-automated process to identify the duplicates. At first, a rule-based heuristics tried to find a duplicate candidate for each new record. And then a team of data stewards used to review the algorithm results, but also to look for duplicates manually. Unfortunately, the heuristics performed rather poorly, and most of the work had to be accomplished fully manually. Therefore, it required replacement as it was a very time-consuming activity. However, as this process was in place for years, we had access to an extensive collection of duplicated records, and we could leverage this data to build a supervised machine learning model. Once we speak of supervised machine learning for the deduplication problem, the very first idea would be to build a machine learning classifier that, given two records, tells if they refer to the same project or not. So for each new record, we could pair it with all the other records in database and ask the classifier if any of the pairs constitute a duplicate. Obviously, such a solution wouldn't scale up, as it would lead to running the classifier on several millions of pairs for each new input, and we needed something better. For example, we could create a better solution if we transform the database records into some feature space where similar examples are located near each other. It means we could just measure the distance between the points in the feature space to know record similarity. Then each new input could be projected into the space and immediately land near similar records. In such scenario, we could look just in some small range around the projected point and measure the distance to the points in its neighborhood to identify the duplicates. And such approach is totally feasible, and one way of obtaining such an embedding space is to apply contrastive representation learning, which yields precisely the properties we are looking for. The goal of contrastive representation learning is to learn such an embedding space in which similar sample pairs stay close to each other while the similar ones are far apart. In this talk, I'm not going to provide a comprehensive overview of contrastive learning methods, as there are many great online resources, and I especially recommend the blog post linked at the bottom of this slide. During this talk, I will focus only on the approach we took. We decided to build our solution based on the well-known triplet loss function. And just a small recap to ensure we are all on the same page. Triplet loss is a loss function that considers three types of inputs: encores, negatives, and positives. Given an encore example, we try to make the model learn such an embedding space where the distance between the encore and the positive example, that is an example of the same class as the encore, is smaller than the distance between the encore and the negative. And the negative is an example of a class different than the encore. So more precisely, we try to make those distances diverge by at least some margin value. Otherwise, if we try to make the difference just larger than zero, the gradient descent could converge the model into a trivial solution that maps all the data records into the same point in the embedding space, as it perfectly satisfies the loss criteria. But at the same time, it would lead to learning a meaningless representation. In practice, triplet loss is applied on a mini-batch level. So you run the samples through a neural network to convert them into embeddings. And among the embeddings, you identify the triplets and you calculate the loss. However, a question is, how do we select the triplets? The first thought would be to generate all the possible triplets. However, this would generate combinatorially many triplets, and most of them would be useless, as they would contain easy negatives. I mean, the triplets would already meet the loss function criteria, as the negatives would be located further away from the encores than the positives. Hence, such triplets wouldn't produce any training signal. What is more interesting are hard and semi-hard negatives. Hard negatives are negatives that are located closer to the encore than the positives. Meanwhile, semi-hard negatives are negatives situated further away from the encore than the positives, but not further away than some margin value. Okay, so how did we build our embedding model? At first, you need to know that we decided to split our data records entities into two groups: text and numeric entities. Text entities are basically everything we couldn't transform into a continuous or a categorical variable like project titles or company names. Well, you may think that a company name could be a categorical variable, but it appeared that there is a lot of inconsistencies in specifying the names. Hence, creating a direct mapping from text to a categorical variable was a very challenging task. However, we hope to pick it up and revise this concept soon once again. Anyway, we concatenated the text entities into a consecutive string, but still we separated the entities with BERT tokens indicating a new sentence, so that given entity type always appears in the same sentence order in the concatenated text. Then we trade our text entities embeddings model using SBERT, a well-known framework to construct text semantic similarity embeddings. This way, we got nearly all the triplet loss and contrastive representation goodness for free. Once the SBERT model was trained, we started adding the numeric entities. We designed a small few layers neural network with nonlinearity to produce embeddings of numeric entities. The results produced by this network were concatenated with the embeddings produced by SBERT trained in the previous step. And once again, the triplet loss framework was applied. However, to train the MLP network, we relied on the pre-trained SBERT only as a feature extractor. And by MLP, I mean our small neural network to produce numeric features embedding. I mean, at this stage of this small network training, the gradients were propagated only through MLP while keeping the SBERT weights fixed. And this time we had to implement all these steps in PyTorch on our own. Okay, so having the model trained, we could already transform the data records into the embedding space. However, we would still require calculating the distance between the projected records and the embeddings of all other records from the database to identify possible duplicates, or in the other words, to know which records are located close to our projected point. Hence, it still doesn't scale up. So how to scale it up? What we would like to achieve is to narrow the search space. So instead of comparing the record to all the other records, we would instead compare it only to records that are likely to be similar. And one way of achieving this is to apply some kind of approximate nearest neighbor techniques that are offered by frameworks such as Annoy, Face, or even Elasticsearch, starting from version 8.0. However, instead of using approximate nearest neighbor, we decided to exploit the business knowledge, because it's rather unlikely that newly published information duplicates content from a few years back. Therefore, we decided to prefetch only records with a publication date within some time window and identify the duplicates only among prefetched records. This helped to reduce the search space from millions to thousands of data points. A similarity calculation in vector space might be as simple and fast as a dot product calculation. We could quickly identify similar content published in the past. So let's try to summarize how the whole system, whole system interacts and works. Let's say there is a new article coming to the system, and at first it's converted into a structured data record with the help of NER. Then the data records are transformed into an embedding vector, and then we can identify potential duplicates quickly. The duplicates candidates are further evaluated to determine if they are actual duplicates and should be merged as they describe the same project, or alternatively, there is no duplicated content and the new documents described a new project. So from the technological point of view, NER is a Hugging Face transformer. Our neural network uses SBERT and PyTorch. The search for duplicates is performed with Elasticsearch, as it supports embeddings vectors and metadata prefiltering, and human experts are there to take the final decision. The whole solution is deployed on AWS, and for the machine learning part we rely on SageMaker. So what is the end-to-end performance of such solution? First of all, we decided to rely on top K accuracy to measure the performance. It means the system outcome is correct if it contains the duplicate within top K predictions. we decided to rely on top K accuracy as we still have humans in the loop. And we present them the results of our system. This way we can measure how many candidates they need to evaluate to find duplicates if such exist. One more important thing is that the metric was collected only for records known to have a duplicate. The baseline is the previous algorithm that used to produce only a single candidate. Hence, we measure its performance only as top 1 accuracy. Our system offers 74% improvement considering the top 1 accuracy and seems to perform twice better if we consider top 10 results. So what are the next steps? We still have a semi-automated approach and we ask humans to take the final decision. However, one day we could consider replacing humans with AI, like building a classifier to determine if shortlisted candidates constitute duplicates without any human intervention. Another interesting challenge would be to determine if we could be able to build an end-to-end solution to create records embeddings. I mean, instead of firstly training SBERT and then attaching this small neural network, we could have a single model or train both models at once. And we may actually reconsider this idea pretty soon. But firstly, we wanted to deploy the current solution as it already brought a lot of business value. Okay, so let's try to summarize everything. So first of all, I hope that this talk was interesting to you and you managed to learn something useful, or at least you enjoyed this lecture. And if there is something I would like you to remember, there are 3 main points. First of all, data-centric AI is a widespread approach in many commercial machine learning projects that needs to deal with real-world data. Such data is inconsistent, dirty, or even doesn't exist yet, and you need to spend a meaningful amount of time building proper data collection and data preparation pipelines. Secondly, contrastive representation learning might come with help once you work on any kind of information retrieval task, and you cannot build a rule-based system because it's simply impossible to specify such rules, or they would be overwhelmingly complicated. These approaches work well with text, images, or as we've shown, with structured data records as well. And lastly, don't forget to incorporate business knowledge into your solutions, as it may save you a lot of trouble. In our case, we simply used metadata prefiltering to reduce the search space without the need of applying some sophisticated algorithms or third-party libraries. And that's it. If you'd like to learn more or simply stay in touch, feel free to bother me on LinkedIn. I'm also looking forward to your questions. And thank you. That's it.
Firstly, hi Marcin. Nice to see you again.
Hey guys, good to be here again.
Awesome. We've got 3 questions as far as I can see, or even more even. Yeah. So let's start with the most upvoted one by Kamil. Once you finish the data creation process in the named entity recognition task, did you try to improve the results by changing the model, or is it forbidden in the data-centric approach?
Well, I would say that once we're applying the data-centric approach, it's more about keeping the model fixed, and it might be a little bit of exaggeration, but what you try to do is to align the data with your model, right? So you're like trying to prepare the data the way you get the most out of your model. However, yep, after collecting the data, we tried to experiment a little bit with different transformer-based approaches, like distilled BERT, for example. But basically, we couldn't see any significant change in our F-beta 0.5 score. So we stick to distill Roberta base. Apart from that, we also try to play with the loss function, because this is a real data. So basically, once you work with text documents, most of the sentences in those documents doesn't contain any named entities. it means you have a huge class imbalance because most of the sentences, most of the tokens are not assigned to any of the entities you try to identify. But apparently, we tried something like weighting the loss function according to the frequency of our examples. And what's interesting, it appeared that this Roberta base was quite robust to this class imbalance. And even if we played with the loss function, we still couldn't observe like a significant improvement in our model. Yeah, so that's basically it.
Mm-hmm. Now let's go with a question from Alex. Could you elaborate on the space search methods? Were you mainly guided by the scalability in choosing the suitable search space method, or did you keep on golden mean between scalability and quality of the method? Have you tested other approaches, and if so, did they actually work?
Okay, so basically when you are about to select the right approximate method, you need to answer yourself a few questions like if the data is to be fixed or if you are about to insert new records frequently. And then depending on that, you go for the right framework. But luckily, we didn't have to do anything of that because we immediately knew that there are some business rules that largely reduce the search space. And as I mentioned in the talk, we worked with like dozens of millions of data points. And just by applying those business rules, like, looking in some particular time window for similar records, we managed to reduce the search space from dozens of millions to like dozens of hundreds at most. And basically when you run a k nearest neighbor search, because this is basically what we did, it can process those amount of information, well, basically in a blink of an eye, because modern KNN approaches are pretty fast out of the box. But also what's worth mentioning at this point is that we decided to use Elasticsearch because anyway, it was a part of the solution of our client. So it was already deployed, it was already in place. And Elasticsearch offers both word embeddings and secondly, the metadata prefiltering so that we could use it to prefilter the records that we are interested in, I mean, using this time window. And secondly, if we were about to improve the performance in terms of the search time, in terms of reducing the latency, we could also try to play with the setup of Elasticsearch, like trying to adjust the nodes to perform the search in parallel and so on. But also, what makes me really happy, what puts a smile on my face is that Elastic from version 8.0 starts supporting approximate nearest neighbor search. So maybe in the future, maybe if I will have a pleasure to participate Ghost Day in a year or two, I will be able to say we used Elasticsearch 8.0 and approximate nearest neighbor search from there. And yeah, I hope you will be interested in this talk and you will host me in the future as well.
Looking forward to that for sure. 3 more questions, 2 from Daria. The first one, did you involve any feature engineering comparing the model performance depending on the input features we use? Maybe some entities could be useless, the annotating process could be simplified.
Yep, we did. We did because initially we started with a very basic model, like a few layers, multi-layer perceptron, and we quickly identified that some of the weights got zeroed for some of the features. So we decided to exclude them from the training set. So yeah, we did this kind of operation. Plus also what we did was like in the process of data collection, we try to monitor the amount of data of given type, I mean, the amount of examples of given entities, plus also its quality, like the consistency that I mentioned. And for example, I remember we had an entity that was, well, so ambiguous that I bet there is no machine learning model that could deal with identifying this kind of entities. So it was like I would say a little bit of both, a little bit of data preparation and incorporating business knowledge, trying to understand which entities are suitable for machine learning at all. Plus, we also did some feature engineering, trying to determine the importance of entities and identify those that doesn't bring any value for the model.
Awesome. Actually, 3 more questions. Keep coming. Another one from Daria. Was the named entity recognition necessary? Could you use SBERT on the whole text?
Yeah, this is a funny question because I expected this one. Okay. Look, basically, the text that we dealt with was pretty long. If I say that approximately this was like A4 page long text, I wouldn't be much wrong. And we weren't particularly interested in this text as a whole. We are more interested in those particular entities that define the project and are important from the business perspective. And the rest of the text would contain sentences without any named entities, like, you read an article and most of the sentences are like some, let's say, human pleasant sentences so that you can read it fluently and there's like this natural flow of reading. But from our perspective, they were useless. And as anyway, we had to extract the named entities and store the data as the data readers, because this is like the core of the business of our client. They extract this data and they analyze this data and they sell those insights further to their customers. We had to build this NER anyway. So why not to benefit from the data that is already pre-extracted? And this is what we did.
Another question on SBERT. How did you use SBERT with 2 different encoders? That's a question from Jakub.
2 different encoders? I think I don't quite get this one.
Okay.
I can tell you how we used SBERT, but I don't really get the part with 2 different encoders. So.
Right. Yeah, maybe Jakub, you could specify the questions on the chat. I see that Marcin is there, so probably you could elaborate on that there. And we have a question here on our internal chat from Tomasz Marcinek, our previous speaker, and the question goes like that. You mentioned overall improvements. It also seems that the new approach included a number of different techniques modification. Did you try to figure out which of the techniques you introduced actually led to the improvements? Can these winning techniques be isolated and tested individually?
Yep. On the table I presented, it's like doesn't cover the full testing we did. I presented only 3 approaches. The baseline, then I presented the gain we got by applying only the text name entities and building the model on top of these text entities. And then the final performance once we added the numeric entities. And from what we can read from that table, it appears like the biggest gain was brought by the text entities. And my gut feeling is that it's mostly related to the descriptive named entity that is project title. I believe that project title is the one that like keeps the most of the discriminative information. So based on the project title, you can already judge if something is a duplicate or some other record or not. And I believe the biggest gain is mainly to learning the semantic representation, the semantic meaning representation of the project title and the extra named entities.
Awesome. Thanks, Marcin. That concludes this session. That concludes this presentation. Thank you very much. And
Thank you very much.
Right. Awesome. Thanks for your contribution.